Swayamprabha. Digital India. Educated India.
We have been discussing on various aspects of low Reynolds number hydrodynamics, and so far we have considered only internal flows, that is flows taking place through channels or ducts. These kinds of examples we have primarily considered, although we have considered some cases of external flows with regard to unsteady flows. We have considered some cases of flows over flat plates and so on, but mostly we have considered internal flows. Now, external flows are important in the microfluidics context because of several reasons, right. Let us consider an example of, let us say that there is a charged species. This charged species is moving, say this species has a negative charge, this charged species is moving under the action of an electric field. So, let us say there is a fluid medium, there is an electric field that is applied on this. Let us say that Q is the charge. So, if Q be the charge and if E be the electric field, then Q into E is the force that is acting on this charged species. Now, if the charged species is not accelerating, then what is happening? That this driving force should be balanced by the viscous drag force. This must be equal to F drag, and this drag force is a function of the relative velocity between the fluid and the charged species. Okay. So, what is the velocity at which this charged species will move relative to the fluid? That will be decided by what is the drag force on this particular charge species. And to know what is the drag force on the charge species, we may consider several situations. Now, one idealized situation is an idealized model of the charge species, where the idealized geometry may be, for example, spherical geometry. Now, you may argue that spherical geometry may not represent all the charge species, and that is true, right. While spherical geometry may represent some of the ionic species, a spherical geometry may not represent charge species like DNA, for example. So, if you want to go for a very accurate model, you have to consider the shape, the geometrical shape of the charge species. However, for simplicity, for many complex shaped objects, you may consider them to be of some equivalent radius, where the radius defines the radius of an equivalent sphere, and that radius can be thought of as the radius of gyration of the system. So, if you are trying to model the situation by an equivalent sphere or sometimes maybe equivalent cylinder, we will take that example of a equivalent sphere. Then for the equivalent sphere, it may be possible that we can calculate the drag force by using simple analytical tools, and that is a very classical problem. Of course, for more complicated shaped objects, we can follow the same governing equations, but the same kind of analytical solution will not hold and numerical solutions may need to be obtained for complex shaped bodies. So, the idea is that we are interested to calculate the drag force on a body of idealized geometry that is there moving relative to the fluid. Now the question is, how is it moving? Now we are typically considering low Reynolds number hydrodynamics. So we are considering that the Reynolds number based on the diameter of the sphere is pretty low. So I mean typically the Reynolds number much less than 1, so that viscous forces are dominant as compared to the inertial effects. So our objective for today's lecture is that we have, let us say, a sphere in a low Reynolds number background flow. So it does not matter whether the fluid is stationary and the sphere is moving, or the sphere is stationary and the fluid is moving, because it is the relative velocity that matters. So let us say that the sphere is stationary and the fluid is moving past it, and the typical Reynolds number based on the diameter of the sphere is low. So for that particular purpose, what we can do is we can refer to a very classical problem which was solved by Stokes long back, and the idea of the classical problem is to solve the velocity profile, the pressure profile, and hence the drag force that is acting on this spherical object as you have a low Reynolds number fluid flow past the same. The Reynolds number of course is classically calculated based on the diameter of the sphere. Okay. Now we will stop solving this problem at this stage, because this problem will require the use of a coordinate system with which you may not be that familiar with. So we will start with an equivalent problem description which we will represent in terms of a vector notation for any arbitrary coordinate system, and then we will specify the particular case for this type of coordinate system. So to do that, let us say that we are interested to write the governing equations of motion in terms of the Cartesian coordinate system. Okay. So now in terms of the Cartesian coordinate system, let us say we write the Navier-Stokes equation. Although it is low Reynolds number, I am still writing the full form just to give you the form of the Navier-Stokes equation in vector notation. We are considering incompressible flow. I am not adding any body force here. I mean, you can add the body force in the way in which you like. So now you can write this term V dot del u, because this V dot del is what? This V is ui plus Vj plus Wk, and what is this del? I del del x plus j del del y plus k del del z. Okay. So, if you take V dot del, it becomes u del del x plus v del del y plus w del del z, and the operator is operating on u. Okay. So, this is the x component of the momentum equation, x momentum. Similarly, y momentum and z momentum, let us quickly write. Y momentum it will be v dot del v. And the z momentum okay. Now what we do is we consider this into I cap, where I cap is the unit vector along x, this into j cap and this into k cap, and add. So, that gives the vector sum of the 3, and if you do that, then what you get? Rho del del t of u I cap plus v j cap plus w k cap. So, capital V vector plus v dot del v dot del u I cap plus v j cap plus w k cap. So, that is V is equal to minus I del p del x, j del p del y, k del p del z. So, minus grad of p plus mu del square of, so see here the operator is Laplacian operator, del square del x square plus del square del y square plus del square del z square of ui plus vj plus wk. So, this one, right. So, this is a compact way of writing the Navier-Stokes equation in vector form. We have seen how to write it in index notation. This is a compact way of writing that in vector form, and writing that in vector form like index form is very much specific to Cartesian nature of the indices. So, Cartesian tensor notation. I mean the vector form, the advantage is that it does not require the description of any coordinate system. So, you can use it for a very general case, and if you have a body force, just add a plus b vector for indicating the body force. Okay. Now, for low Reynolds number, you can drop the LHS. We will see later on whether the same is justified or not for the case that we are investigating, but for the time being it is intuitive that if it is a low Reynolds number flow, then the left hand side can be dropped. This is what we have learned from our previous experiences. Now, so far as what we are going to predict whether that particular inference is still working or not, we will discuss about that as we come to the end of the solution of this problem. So, then you have the null vector basically. Now, we will use a vector identity to simplify this problem, but first of all, before using the vector identity, we have to find out a strategy of solving this problem. So, the strategy of solving this problem, see, this equation has 3 components. If we use some other coordinate system, we may reduce the number of components by using some symmetry or that kind of thing, but in a Cartesian coordinate system, see, we are not discussing this specific problem, we are discussing about a general problem that can be described in terms of a suitable coordinate system. We have not yet fixed up the coordinate system. So, this equation involves how many unknowns? In general 3 velocity components and pressure. So, you have 4 unknowns, and for an incompressible flow you have 4 governing equations also. So, that closes the system, but analytically it is very difficult to couple the continuity equation with what? With the momentum equations, with the Navier-Stokes equation. Analytically difficult to couple, numerically it is relatively more convenient. So, what becomes the deterring factor? The deterring factor is this pressure. These governing equations are equations governing velocity, but in that extra unknowns in form of pressure appear, but we do not have an explicit governing equation for pressure. So, one possible strategy may be, so our origin of headache is the pressure. So, the solution is, I mean, this kind of solution is a very radical solution. The solution is, if you have headache, you cut your head. So, if you do not have head, you do not have headache, right. So, you have pressure in this equation, so you somehow eliminate pressure, then there will be no problem with the pressure term. So, how can you eliminate pressure from this equation? So, one simple strategy is, if you take curl of both sides, you can use the vector identity that curl of grad of a scalar is a null vector. Okay. So, this will go away. Okay. So, take curl of both sides. So, if you take the curl of both sides, this becomes 0, Now we will use a vector identity this is a very commonly used vector identity, and the interesting part of the vector identity is that you have a divergence of velocity in one of the terms. So, if it is incompressible flow as we are considering for this case, then this term will go away. For incompressible flow, not for all cases, only for incompressible flow. So, instead of del square V you can write minus del cross V. Right, using this identity. And what is del cross V? What is the curl of the velocity? That is nothing but the vorticity. So, let us, this is vorticity, let us say the zeta we use for vorticity. Okay. So, we can write this is curl of vorticity, and we have additionally taken a curl to make this term 0. So, that is why curl of this. Now, we can now use the same identity here, just replace V with zeta, right. So, we can write okay. Just I mean here instead of V we are using zeta. Now, what is this? This is del dot del cross V, and by a vector identity this is 0, divergence of curl of a vector, this is 0. So, we are left with del square of zeta is equal to 0. Now, let us consider an example of a two dimensional flow. In Cartesian system, described in Cartesian system. We are starting with the Cartesian system, not because that we will use the Cartesian system to solve the problem of the sphere, but because of familiarity you can understand certain concepts which we will borrow for solving the problem of the sphere. Now, for this particular problem, now for 2D flow zeta this is the scalar component of vorticity. So, for a 2D flow the vorticity vector is having an effect which is perpendicular, the unit vector is perpendicular to the plane of the flow, and the magnitude of the vorticity is this one. Okay. Now, so this is zeta with respect to z axis, the vorticity. Now, for a 2-dimensional flow, see, we had said that for eliminating this term, by eliminating this term pressure, we are not having an explicit linkage of the continuity and the momentum equations, but there has to be some reference to the continuity equation. Otherwise, how do you ensure that you are solving the velocity field from the momentum equation that satisfies mass conservation? That has to be ensured. So, somewhere continuity equation has to be brought into the picture. How we bring into the picture here is by defining this velocity in terms of stream function. So, we define, let us say u is equal to del psi del y and v is equal to minus del psi del x. Okay. So, what are these u and v? These u and v are the velocity components and psi is the stream function. So, you can see that this definition of psi automatically satisfies the continuity equation del u del x plus del v del y equal to 0 for 2-dimensional incompressible flow. So, you can write zeta z now. For defining the stream function, we have to be careful that u and v have to be carrying opposite algebraic sign. So, it does not matter, I mean here we have taken this as plus, this as minus, but we could have easily taken this as minus and this as plus, that would have made no difference. So, this is in 2D, this is minus del square psi. So, del square zeta z is equal to 0, that means you have del square of del square psi equal to 0, right. This is what we learned from our 2D experience, 2D Cartesian. Now, let us come to the problem of the sphere, flow past the sphere, low Reynolds number flow past the sphere. So, if you now use a coordinate system which is radial r and angular coordinate theta, then instead of u and v, you could use the components Vr and V theta, but because of the change in the coordinate system, then this del square operator will not work. So, instead of del square, we will use a different operator which is called as E square operator. We will come into that. So, just try to understand the analogy of the concept. The operator is simply different because we have to adapt to a different coordinate system, but concept wise it is very similar. So, E square of E square psi will be 0, and this psi is not the normal stream function in the Cartesian system, but the stream function defined for this coordinate system, which is also called as Stokes stream function. With this background, the definition of stream function will be different, but that will satisfy. Why it has to be different? Because that has to satisfy the version of the continuity equation for incompressible flow in the r theta coordinate system. not the Cartesian system. Now next, what we will do is, we will try to assess that what will be the velocity field far away from the sphere. See, we intuitively expect that far away from the sphere the effect of the sphere will not be important. So, the velocity field, if this is u infinity, that will again become u infinity far away from the sphere in the downstream. So, if you have this as Vr, then this will be the V theta and this is the resultant which is u infinity. This angle is theta and this angle is 90 degree. So, technically at r tends to infinity, you have Vr is equal to u infinity cos theta and V theta is equal to minus u infinity sin theta. Why minus? Because positive theta direction is opposite to this V theta direction, right, if you see this vector triangle. Okay. So, now the next step is we will write this Vr and V theta in terms of the Stokes stream function, and then we will solve the stream function, we will find out the stream function at r tends to infinity. So, we need to now express Vr and V theta in terms of the psi. These expressions what we are going to write for the r theta coordinate system are quite involved. I mean, it is very difficult to remember this, I never try to remember this. I mean, it is up to your wish, you may try to remember this, but that will not give you any credit. At least if you are thinking of getting Nobel Prize, you will not get Nobel Prize by remembering r theta coordinate system equations. So, I mean, we will just write the standard form of the equation Vr as a Vr and V theta as a function of in terms of psi, the Stokes stream function and theta, and then we will proceed. So, I am not writing from my mind, I am writing whatever is there given in the slide, I am just copying from there. So, do not think that, right, this is to be written by memorizing, it is not necessary. If these things are to be written or these things are required in some place, some examination or somewhere, assume that these things will be provided, rather you apply your mind for analyzing the problem. So, now Vr is equal to 1 by r square sin theta del psi del theta. So, which is equal to u infinity cos theta at r tends to infinity. So, if you integrate this, so psi is equal to u infinity r square, it is sin theta cos theta d theta. So, let us say that sin theta equal to some z, so cos theta d theta is dz. So, it is integral of z dz, that is z square by 2. So, that means u infinity r square by 2 sin square theta plus what? See, we have partially integrated with respect to theta. So, function of r is like a constant. So, plus a function of r. Remember, this is at r tends to infinity. Okay. We can write a similar expression for v theta. Is equal to 1 by r sin theta del psi del r, which is equal to minus